So for part A, to find the ball's instantaneous speed 25 degrees below the initial release point, I'm going to set the change in PE equal change in KE, because what's lost in potential energy must be gained in kinetic energy. So mgh is equal to 1/2 mv squared. And then for h, I'm going to sub in L sine theta, because this length here is L. L equals 3 meters, since the length of the string is constant. And then the h, the height that it travels, the 25 degrees below the initial release point, is L sine theta, because opposite, is equal to 1/2 mv squared. I'm going to cancel out the m's since it's the same ball. And then GL sine theta is equal to 1/2 v squared. Isolate for v. So I'm going to multiply both sides by 2. And then, isolate for v squared, multiply both sides by 2. And then to get just v, I'm going to square root both sides. And so I get square root 2gl sine theta. I'm just going to plug everything in. L is 3 and it's 25 degrees. So V is equal to 4.98 meters per second. So for part B, to find the acceleration, A net is equal to the square root of centripetal acceleration squared. A net is equal to the square root of centripetal acceleration squared plus tangential or linear acceleration squared, because Pythagorean theorem. And so I'm going to do here, AC is equal to V squared over R. And then we get this from FC is equal to MV squared over R, F equal MA. So to get A alone, you just divide both sides by M to get AC. Okay, so AC, we found V at 25 degrees below the initial release point already, and this is just a net 25 degrees below. So just gonna plug that in, 4.98 squared over R, and R is just 3 because that's the length of the string. And then you get 8.283 meters per second squared when you plug it in. And so that's AC. And ATAN, so ATAN, so this is mg. ATAN will be moving this way with the motion. Oh, that should be dotted. FGX. Wait, oops. This is FGX. This is FGY. Sorry. But because this moves with the motion, this is what is going to cause it to accelerate. And so just based on geometry. FGY is equal to mg cos theta. And then I'm going to set this to MA, and this is MA. Oh my god, that's ugly. FGY is equal to mg cos theta. Mg cos theta is equal to MA tan. And then just isolate for A tan, I'm going to divide both sides by M. So A tan is equal to G cos theta, which is equal to 9.8 cos 25 degrees. And that makes A tan equal to 8.881 meters per second squared. So A tan is equal to 8.881 per second squared, and I'm just going to plug that into my A net. So here. Is equal to AC squared, so 0.28 squared plus 8.881 squared, which is equal to 15.474 meters per second squared. And this is magnitude, so I'm not going to put any direction. Okay. For part C, A linear is equal to angular times, so A linear is equal to the angular acceleration times the radius, and like I said earlier, it's just 3 because that's the length of the string. And A linear, I'm just going to use A net that we found earlier, 15.474 equals alpha times 3. Alpha is equal to 15.474 divided by 3. Therefore, the angular acceleration is equal to 5.158 meters per second squared. And again, this is just the magnitude, so the direction. And also, because it's at 25 degrees, I could just use this. Again, I forgot to box this. Okay, so this is me redoing part D, because when I found V at the bottom to plug in for FC, I meant to keep things in terms of V squared, but then I accidentally did the square root of it, but then I still got the right answer when I plugged it in, because I was referencing my old, or like my original work, like my practice work, so yeah, oops. So for part D, to find the tension just at the bottom of the string, just before it strikes the block, I'm going to set up net forces. So T minus FG is equal to FC. I'm going to break FG and FC up. So T minus mg is equal to mv squared over r. This is actually v at the bottom because it's just before it hits the block and the string is fully extended. Therefore, all of the potential energy has been converted into kinetic energy because it has traveled the max height it could go. It's gone to initial release to like the very lowest it can swing. So I'm going to set mgh is equal to 1/2 over mv squared. I'm going to cancel out the m since they're the same. GH is equal to 1/2 v squared. Isolate for v by multiplying by 2 on both sides, so v squared is equal to 2gh. And then therefore v squared, I'm going to plug in g and h. H is 3 since it's fully extended, and that's the length of the string. So this is equal to 2 times 9.8 times 3, which is equal to 58.8 meters per second. And then v is equal to square root of that. This is v squared. Regular v is equal to 7.688 meters per second. But now I'm just going to plug this in over here, and then r is just the length of the string, and m is the mass of the ball. So t minus 1.8 times 9.8 is equal to 1.8 times 58.8 over 3. I'm going to move this over. T is equal to 0.8 times 9.8 plus 1.8 times 58.8 over 3. And then once you simplify that, you get T is equal to 52.92 newtons. Yay. So yeah. So when I reference this, I actually just mean V, not V squared. This is just V initial of the string of the mass of the ball just before it strikes the block. For part E, I'm going to start by setting up conservation of momentum. So the initial net momentum is equal to the final net momentum. And this is the same as m1v1I plus m2v2I is equal to m1v1f plus m2v2f, and then I'm going to set the subscript 1 as the ball and then subscript 2 as the block. So this will be 0 because the block is initially at rest. And then v1 initial we found in part B at 7.668 because as the ball swings from the initial release position to fully extended, just before it hits the block, all of the potential energy will be converted into kinetic energy. And I did that here. So I'm just going to plug everything in. 1.8 times 7.668 is equal to 1.8 v1f plus 0.4 v2f, and this is 13.802 is equal to 1.8 v1f plus 0.4 v2f. And then I'm going to actually isolate for v2f because later when I do the conservation of kinetic energy, since this is perfectly elastic, I can do that. I want all of my terms or all of my variables to be in terms of v1f, and I do not want two variables when I solve, since I'm solving for the velocity of the steel ball immediately after the collision. So I'm going to subtract both sides by 1.8 v1f. and then I just rearranged it a bit, but it's the same thing. And then I'm going to divide both sides by 0.4, and I get V2F is equal to 34.802, 506 minus 4.5 V1F. Sorry, and now I'm going to set up conservation of kinetic energy. So, of the system. So, 1/2 m1 v1 I squared is 1/2 m2 v2 I squared. That's equal to 1/2 m1 v1f. Oh, why is that so little? Squared equal, plus 1/2 m2 2f squared, and again this is 0 because the block is initially at rest. I'm going to plug in my m1 and then my v1 initial and then all my other two m's. Oh wait, no. First, I'm going to cancel out the 1/2 since it's just a constant and it's all the same. And then I'm going to plug in my masses and then v1 initial. So 1.8 times 7.668 squared is equal to 0.8 v1f squared plus 0.4 v2f squared. And then I'm gonna simplify this. So 1.8, this is 105.84 is equal to 1.8 v1f squared plus 0.4 v2f squared, parentheses, and then v2f, I'm just going to plug this in, but this is squared, so I'm just going to square over here. So v2f squared is equal to 4.506 minus 4.5 v1f, 34.506. So this squared is just the same as multiplying this whole thing by itself. So now I'm just gonna FOIL that. 34.506 times 34.506 is equal to 1190.7. And then I'm gonna do 34.506 times negative 4.5 v1f minus 155.279 v1f, and then negative 4.5 times 34.506 again. It's just the same thing. 279 v1f, and then negative 4.5 v1f times negative 4.5 v1f is equal to positive 20.25 v1f squared. And then, so this is v2f squared. I'm just going to distribute the 0.4 here. So .4 v2f squared is equal to this times 0.4. So I'm going to combine like terms on the inside. Minus 310.55. And then multiply everything by 0.4. I get 0.1 v1f squared plus 124.223. So this is what I get for 0.4 v2f squared. And then I'm just going to plug this in back up there. So 105.84 is equal to 1.8 v1f squared plus 8.1 v1f squared plus 124.223 v1f plus 476.28. And next I'm going to combine these two like terms and then move this over. Combine these two so I can set it equal to 0. This is tiring. 0 is equal to 9.9 v1f squared, or plus 124.223 v1f plus, plus, oh, yes, plus 370.44 is equal to 0. So then, oh, why did I set it equal to 0 twice? Yeah. So this whole thing is equal to 0, and now I could do the quadratic formula. I could do the quadratic formula to solve for v1f, and just put it in the calculator. And for that, I get d1f is equal to 0.879 meters per second and 7.668 meters per second. And it gave me two x's, or two answers for my variable v1f, and it's definitely not this one, because that was the initial velocity of the ball right before it hit the block. And according to the conservation of momentum, there's no way my initial velocity could equal the final velocity of the ball if there's also another block that's moving. Like, yeah. So yeah, v1f, the final velocity of the ball is positive 4.879 meters per second. Okay, so for part F, to find how much time it will take for the block to come to a stop. So for the block, I'm going to set up VF is equal to AT plus VI, which is one of the kinematic functions. VI, I'm going to reference after the collision. So, because that's when it starts like actually moving. So VI will actually be V2F from our previous problem, part E. So I'm gonna use this. V2F is equal to 34.506 minus 4.5 v1f equal to and then we found v1f earlier as positive 4.879 meters per second. And then you get v2f is equal to 12.54, positive 12.54 meters per second. And then, like I said, I'm going to reference this as my initial velocity once it starts moving. This is also my vi. And then I'm going to set my final velocity equal to 0, because when it's at a stop, vf is 0. At plus 12.54. And then to find a, I'm going to set up net force. So it's equal to m times a. And then in this case, the only force acting on the block is the force of friction. It's equal to ma, and this is equal to mu kmg equal to ma. And then it's the same mass, the same block, so I'm gonna cancel that out. And then I get this. And then so 0.4 9.8 is equal to a, and therefore a is equal to 1.56 meters per second squared. I'm going to plug this in over here. 0 is equal to 1.568 t plus, negative, sorry. It'll be negative because the force of friction is acting against the block, which is causing it to slow down and eventually come to a stop. 12.54. I'm going to isolate for t by subtracting both sides by 12.54. 568. And then I'm going to divide both sides by negative 1.568. And when I do that, I'll get t is equal to 8.002 seconds. So it'll take about 8 seconds for the block to come to a stop. Okay, so for part G, to find the angular speed immediately after the collision. So since the horizontal surface has now been trimmed down to 3/4, and there's now a rod at the end of the 3/4, which the block will stick to once it strikes. And so because it sticks, this is an inelastic collision, and it tells me to treat the block as a point mass. So for part G, I'm going to set up conservation of angular momentum, which is also equal to momentum times the arm of r, or just like you do perpendicular, basically, which is equal to inertia times omega, and the omega is what I'm trying to find immediately after the collision. So I'm going to set m1. M1 will be the block times v1f, because that will be the the speed right before it hits the rod, which is equal to I omega, inertia times omega. And then I'm going to find the total inertia, so it'll be 1/3 ml squared plus the point mass of the block, m2 for the rod, m1 r. Oh, I forgot an r. Oh my gosh. Okay, so it's m1 v1f times r, which is equal to I omega, oops, sorry, times r squared times omega. So I'm trying to solve for omega, and r is just 2/3 times L, so 2/3 L. And then I'm just gonna solve for that. L is 5, so that is about 3.33 meters. And then I'm just going to plug in for my known variables. So this is 0.4 v1f times 3.33, which is equal to third, what is the mass? 1.1 times 5 squared plus 0.4 times 3.33 squared times omega. And now everything else they're known values, they're numerical, but I have this as an unknown value because the block no longer comes to a stop since it's not traveling the full distance. It's going 3/4 of the original distance, so it'll still have velocity when it strikes the rod. So I'm just gonna solve for that now. So originally I'm just gonna use common form. X, so I'm going to use common form to find the distance between the original horizontal surface distance. So 0 minus 12.54 squared, which we found earlier, is equal to 2 times negative 1.568 to x, and then I'm going to isolate for delta x. And then once you simplify this, you get delta x is equal to 50.21 meters. And then to find the final velocity of the block just before it strikes the rod, so it'll be 3/4 of the original distance. So I'm going to set VF squared minus 12.54 squared, the initial velocity of the block just as it starts moving after it's been struck by the simple pendulum. So this stays the same. It's equal to 2 times negative 1.568. That acceleration stays the same. Times 3/4 times 50.21, because this is 3/4 of the original distance. And then I'm going to isolate for VF squared, and I get actually I'm going to distribute the square, and then I'm going to simplify the right hand side. VF squared is equal to, oh my gosh, sorry, VF squared minus 157.25 is equal to negative 118.086, and then I'm going to isolate for VF squared by adding 157.25 to both sides, and I get 39.36. Square root both sides to get VF, or V1F, same thing, or VF in this case will be my V1F for angular momentum, which is equal to 6.27 Oh, here, I'll do this. Meters per second. And then I'm gonna plug this in over here. So 0.4 times 6.27 times 3.33 is equal to 1/3 times 1.1 times 5 squared plus 0.4 times 3.33 squared omega. I'm gonna simplify both sides. And this is what I get. And then I'm going to solve for omega by dividing both sides by 13.61. And I get the magnitude of omega is equal to 0.615 rad per second. Okay, so for part H, to find how high the rod block system will rise after the collision, I'm going to set my change in PE equal to my change in KE, because what's lost in KE as the block was lost in kinetic energy as the block rod system rises must be gained in PE. So I'm going to do mgh is equal to 1/2 I omega squared, but this is m total because it's the block plus the rod. And then this is only rotational kinetic energy because the system is not moving linearly, it's rotating. So m total, that will be m block plus m rod times gh is equal to 1/2 I omega squared. And then I'm going to break down the inertia. One-third ml squared plus 2/3 plus, this is mr mb times 2/3 L squared times omega. And because this is where the block hits the rod. And then I'm just gonna plug everything in. So 1.1 plus 0.4 times 9.8 times h is equal to 1/2 times 1/3 times 1.1 times 5 squared plus 0.4 times 2/3 times 5, which is our L squared, is equal to omega. Times omega, not equal to omega. It's 1.1 plus 0.4 times 9.8 times h is equal to 1/2 times this whole thing times omega, but omega, as we found earlier in part G, omega is equal to 0.615. This should be omega squared. So I meant to plug that in. Oops. I'll plug that in now. Oh my gosh. Okay, and then now I'm just going to simplify both sides. so that I can solve for h. And then I get this, and then I'm just gonna simplify this side. And then divide both sides by 14.7 to find h. So h is equal to 0.175 meters. So this is the height the rod block system will rise after the collision. Okay, so for part I, the angular speed of the rod block system would change to a decrease. So the angular speed would decrease if the rod is lowered and the block strikes it at L/2 instead of 2/3 L, because, okay, so I first thought of this as like torque. So there's going to be the force of the block hitting the rod, which will cause it to rotate, and then torque is equal to F force times the cross product of R. And then so there's the force coming from the block as it hits the rod, which causes it to rotate and move, and then it'll be times the perpendicular distance because it's cross product. And then so because this force will stay the same and only the length of the rod and like how far the block is hitting it will change, because R is decreasing to 1/2, the torque will decrease and therefore the angular speed will decrease. So that's how I thought of it, but you could also do it mathematically by setting up conservation of angular momentum again. So you would do and then mvf times r is equal to I double times omega, and then that's just like what we did in part G basically, but then I'm going to replace, so VF or V initial of the block as it starts moving after being hit will stay the same, mass will stay the same, so it'll be 0.4 times 6.27 times R, which is now 1/2 times 5 because it's L/2 and L is 5, which is equal to 1/3 m. Oh my gosh. Times 1.1 times 5 squared plus m is 0.4 times 1. Oh, that should be 1/2 times 5 squared times omega, and then I'll simplify for both sides and get 6.27 is equal to 0.67 omega, and omega, when I isolate by dividing both sides by 11.67, omega nu, this will be our new omega, equal to 0.538 rad per second, and this is less than the original 0.615 rad per second, so therefore it will decrease. Okay, so for h to find the period, I'm going to set up the equation for period of a physical pendulum, because that's what this is. It'll be it'll be 2 pi times rad I total over mgd, and d is the distance from pivot to center mass. So we know 2 pi, we know the total mass, we know g, and we don't know d. I total, we found in part D already, and we did this by just setting up 1/3 ml squared plus the point mass of the block. Let's exclude that, and that's just 13.61. Our total is equal to 13.61. So to find the distance from the pivot to center mass, the pivot is actually just the end. So to find center mass, I'll do it here. I'm gonna set m1 times x1 plus m2 times x2 over total mass, which is m1 plus m2, and I'm going to set m1 as the block, not the block, the m1 as the rod, m2 as the block. So now I'm just going to plug everything in. So 1.1 times x1, that's just the length of the rod, plus 0.4 times x2, and it hits the block, the block hits the rod 2/3 L from the pivot, so that's 2/3 times 5 over 1.1 plus 0.4, and then once you simplify all that, you get center mass is equal to 2.72 meters. So, and I forgot to mention, this is m total. M total is equal to 1.1 plus 0.4, which is equal to 1.5. Now I'm just going to plug in all these values into this equation. So T is equal to 2 pi times radical I total 13.61 over, where's my mass? 1.5, 9.8 times 2.72, and the center mass just so happens to be the distance from pivot to center mass, just because the pivot is at the end. So once you simplify this and plug it in, you get T is equal to 3.66 seconds. Yay, I'm done. Goodbye. Wait, can you focus?